So, today we are starting rigid body dynamics, and you have done some rigid body dynamics in schools, and especially with a fixed axis of rotation. A rigid body, as you know, is rigid. Ideally we assume that it is rigid, although nothing is rigid in this world, but then the definition would be that separation between any two particles is fixed in that body. Now, a general motion of this body is a translation and a rotation. For example, if I have this piece of pen here, and if it goes from here to here, then it has been displaced, its center of mass has gone from here to here, that is translation. And then on top of that there is a rotation, because it was in this orientation and here it is in some other orientation. So, this is rotation. So, this is rotation with one point fixed, whereas this is translation, as if everything is translating. So, if you have any rigid body, and you can start with the center of mass here, and then let me draw, say it is like this, and then when it goes here, center of mass reaches here, and this whole thing gets rotated. So, it is of this type, copy it and rotate. Okay. So, it has rotated as well as it has translated. So, consider any point, any particular point of this, let us say this point and this point reaches here. So, velocity of this point at any time can be written as velocity of the center of mass and plus some omega times position vector of this particle with respect to that center of mass frame. So, you fix up a frame with the center of mass at the origin, and in that frame this is rotating, it is a pure rotation, and pure rotation can be described by this, because if you have an axis here and then a pure rotation, every particle goes in a circle, and you can work out that if this is omega rotation axis, and then you take origin here or anywhere, and then you can see that this r vector and this omega vector, the cross product is v. How can we see it there? Omega cross r, this will be omega is omega in z direction, suppose this is z direction, and we will use cylindrical coordinates. So, r, this r vector is, this is, let us say z. So, z in k cap direction and plus this one is s in s cap direction. So, and this, when you do k cross k cap cross k cap is 0, and you have omega into s, and then it is phi cap, and this is s, and therefore, this omega times s the velocity and phi cap is the direction. So, it correctly gives direction as well as the magnitude. So, this gives you the translation part, this gives you the rotation part about the center of mass. Now, very interestingly, if you do not use center of mass and fix up some other point, say some other point here, let us say some say x, this point is named as x, you can still write velocity of this arbitrary point a, velocity of a at any instant, remember going here to here is a lot of variations. So, at any instant, what I am doing is I am writing the velocity of this particle at some instant, and that will be equal to velocity of this point x and plus omega cross, and then the position vector of this particle a with respect to that x. So, it is not necessary to have the center of mass, you can have you can choose any point you like. You can choose any point of you like, and the translation can be seen with respect to that point going from one place to other place. The whole rigid body is going like that, and then the rotation about that chosen point x. So, you can write this kind of relation not only for center of mass, but for any point fixed in the body. And the most interesting part is that this omega and this omega are same. Omega is same irrespective of the choice of x. You take any point and then you write the velocity of a particle, any arbitrary particle of the rigid body, as velocity of that chosen point plus omega cross position vector of the particle from that chosen point, and this omega remains the same. So, it is independent of choice of this. It can be proved, but I am not going to do that, but this is a very, very interesting result. In this chapter, we will be focusing only on this part, not on this part, or this part, not on this part. So, we will have one point fixed about which the rotation will take place, and then we will do the dynamics of it. Now, as in translational motion, the central equation is F is equal to ma, which you write more appropriately dp dt, where p is the linear momentum. Now, for a rotation of a rigid body, the central equation will be torque is equal to dl dt. Here it was force is equal to dp dt, here torque is equal to dl dt. And what is torque? Torque will be summation over I mi ri vector cross fi external. This is our torque. You can write it external torque. Okay. And remember, the linear momentum and the torque both are defined about a point which we can choose. We have done it during the central motion discussions, that this torque has to be r cross f. Now, from where this r is taken? Our own chosen origin, and depending on where I choose the origin, this torque may be different. That is not the case with f. Okay, f. Similarly, the angular momentum. The angular momentum L is summation over I mi ri cross vi or ri cross pi. This also depends on the choice of the origin. That is not the case here. Linear momentum of a particle does not depend on the choice of the origin, but angular momentum, yes. So, be very careful. The angular momentum has to be calculated about that point, and the torque has to be calculated about that same point, and then torque is dl dt. And this gives me the law of conservation of angular momentum. If external torque is 0, total external torque on the body is 0, then its angular momentum is constant, does not change with time, that is it. And you can show this because when you write L, L is summation over I, here it is mi and then ri cross vi, or you can write pi here, no problem. And if I differentiate it with respect to time, this will be equal to summation over I mi and then ri cross differentiation of this will be acceleration of ith particle, and then plus differentiate this, that will be vi and cross vi. All right. So, we are differentiating this expression summation over I mi, and now we have to differentiate this. So, keep this ri as such and differentiate this vi and you get ai, and then you keep this vi as such and differentiate this r(i) position vector, that gives me again Vi. So, this part is 0. So, what I am left with is summation over I m, or let me write Ri here, and cross mass times acceleration, which is force on the ith particle. Okay. But that does not prove this relation that dl dt is torque external. This is external torque I have written. That means the torque by the forces by objects outside that rigid body, not part of the rigid body. So, that is what I am calling external. So, if you have a rigid body and then you have a particle here, there are various forces on this, some are applied from outside and others are applied by these other particles. So, this particle is maybe attracting, this particle is maybe attracting, this particle is attracting, this particle is attracting. So, these are the internal forces on this particle. Okay. So, our conservation law will be, if torque external is 0, then L is constant. This Fi is the resultant force, because I am writing it for Mi and Ai, So, this is the resultant force on the ith particle. So, this is Ri cross Fi external and then plus Fi internal. And this is summation over I, mass is Lt here. So, Ri cross Fi external, this is one part, this is the external torque, this is that external torque that I am writing here, but then there is another term, summation over I, Ri and cross Fi internal. Now, it is true that if you add all these internal forces on ith particle, you may get some non-zero value. But then when you sum over this I and take this particle also into consideration, this particle also into consideration in this sum, then suppose this particle, now this particle is also attracting it by that same force, this is attracting here and this is attracting here, and that sum will be 0. So, total summation on Fi internal over all the particles will be 0. That is fine, that is Newton's third law. These two particles are attracting or repelling or doing whatever, and the magnitudes are same, the directions are opposite. So, if you divide this whole sum as pairwise, this pair, that pair, that pair, that pair, that pair, that pair, then the total will be 0. But that does not tell me that this is 0. If this sum is 0, that does not mean necessarily that this sum is 0, because every time you are making a cross product and then adding, right. But this happens to be 0 because if I look for this term, summation over I Ri cross Fi internal, what is this? This is force on the ith particle by all other particles of the rigid body. And so, this itself is summation over j, which is not equal to I, and then F I j. Okay, what is this F I j? Is the force on the ith particle by the jth particle, and then we go for all the values of j for second, third, fourth, nth particle except this I, because I have to consider forces by the other particles. That is why this j is not equal to I. All other j I have to consider, and then this total, this quantity is this quantity. So, this you can write here, this j can be taken here, summation over j. So, I have to sum over j and sum over I, j going from 1 to capital N, I going from 1 to capital N, but make sure that you do not put j equal to I, and here it is R I and then cross F I j. Now, this quantity this quantity. Now, consider one particular pair I and j, ith particle and jth particle, this particular pair ith particle and jth particle. Okay. So, I put some value here and some, let's be more specific. Suppose I am talking of second particle and fifth particle. Okay. So, somewhere in this whole sum I will get j equal to 2 and I equal to 5, and somewhere in this I will get j equal to 5 and I equal to 2. So, these kind of two terms, j equal to 2, I equal to 5, there is something, j equal to 5, I equal to 2, there is something. These two I am clubbing together. What will happen? What will happen? This will be R I and cross F I j and plus R j and cross F j I. This is a kind of pair. So, the same I and j are interchanged, I and j are interchanged. So, this whole sum can be written in terms of such pairs, and this pair is R I cross F I j and minus R j and cross F I j. Here I have used third law, Newton's third law. What? F j I is equal to minus F I j. The force by the ith particle on the jth particle has the same magnitude as the force by this jth particle on the ith particle, but with a negative sign, opposite in direction. So, that is Newton's third law I have used. Now, this is equal to R I minus R j and then cross F I j. Okay. R I vector minus R j vector and cross this F I j is taken common. Now, if this force on the ith particle by the jth particle is along the direction joining the two particles, another restriction. So, I have a particle here, I have a particle here, and they are exerting forces on each other, they are equal in magnitude, they are opposite in direction, somewhere origin is here, this is my R I vector, this is my R j vector, and then what is this vector? This vector is R j minus R I, or this vector is R I minus R j. If the force is along this direction, if the force is along the line joining the two particles, then this vector and this vector are parallel. If this force on the ith particle by the jth particle is along that direction joining ith particle and jth particle, then this and this will be parallel, and then this will be 0, and then I will be sure that this whole thing will be 0. So, this is equal to 0 with the condition that the forces by particles on each other are equal in magnitude, opposite in direction, and act along the line joining the two particles. This is sometimes called strong form of Newton's third law. So, that this form of Newton's third law is needed for this being 0. If this is 0, then it is fine. This is this whole thing is now torque external, and then you get dl dt is equal to torque external, dl dt is equal to torque external. If the total torque by the external forces applied on the rigid body is 0, then the angular momentum is conserved. So, this is important theorem, or this relation itself is very important. This is the central equation of this whole rigid body dynamics, and therefore, let us see what is the relation between this L vector, the angular momentum vector, and this omega vector, because this omega describes the rotation of this rigid body at that instant itself. Okay. So, let me make some space. So, angular momentum vector L, I am talking now of some rigid body, there is some origin somewhere, okay, and then I am talking of some particle, ith particle, and this is position vector r I, and then this particle at this instant has some velocity v I, right. So, angular momentum will be summation over I m I r I cross v I, and v I is omega cross r I. Okay. Velocity is omega cross r, we are talking of that rotation part only. So, any general motion can be decomposed in two parts, translation and rotation, and rotation will have the same omega, translation velocity will depend on which point you have chosen for that reference. So, this is it. Now, you must be knowing this, that A cross B cross C is equal to A dot C and then B vector, and then minus A dot B and here C vector. This you can work out standard result. Any three vectors you take, and in this fashion you do the cross products, and then this is equal to this. This we will be using for this part. So, L is equal to summation over I m I, then this has to go out. So, this dot this r I dot r I and the omega here, and then minus. Now, this has to go out. So, r I and dot this omega, and then this r I here. This is it. This is equal to summation over I m I, and this is r I square, and what is r I? Is the distance of the particle from the origin, this, and then omega. So, this is omega, and okay, fine, omega, and here it is x I omega x plus y I omega y plus z I omega z. I am not taking the z axis along that omega. So, omega will have components in x, y, z direction. So, I am writing this r I as x I cap plus y I j cap plus z I k cap. So, those x I, y I, z I are here, and omega I am writing as omega x I cap plus omega y j cap plus omega z k cap, and then taking the dot product, it is this, and then it is r I. Let us see what is Lx, x component of this angular momentum vector. So, x component, here is vector and here is vector, and I am taking x component, summation over I m I r I square, and then omega x, I am only taking the x component. So, omega x minus x I omega x, y I omega y, these are all scalar quantities, they are not going to change. The component only comes from here, x component, so that is x I is equal to summation over I m I. Let us take that omega x part. Omega x is coming from here, so that is r I square. Then omega x is coming from here, so minus x I into x I and then omega x. So, minus x I square and into omega x. So, this is that omega x part I have taken, plus omega y. Where is omega y? Here is omega y, the only place. So, it is minus y I and x I, minus y I and x I. Okay, just multiplication here. So, I have taken omega y part, and the only term left is this, which is minus, and then z I omega z I will be writing outside. So, x I and this omega z. So, minus omega z. that is it. Alright. So, Lx is equal to, so this is equal to summation over I mi, and then this is yi square plus zi square, this is one part into omega x, then plus omega y part. So, summation over I minus mi minus I have written, and then yi xi. So, let me write xi yi and then omega y, and plus summation over I, that other part, summation over I minus. So, let me write it bracket here and minus here. All right. So, it is mi, and then it is xi zi. So, xi times zi, and that is omega z, that is omega z here. So, that is Lx. So, Lx will involve omega x, omega y and omega z. So, for symbol I am writing this as, let us write this as Ixx, okay, omega x, plus let us write this as Ixy and omega y, plus this is Ixz and then omega z, where I am writing Ixx for summation over I mi yi square and plus zi square. And what is this quantity? This is essentially perpendicular distance square from the x axis. So, if you take the usual moment of inertia of class 11 about the x axis, you will take mass of the particle into distance from the x axis square. So, that is this part. So, this is essentially your commonly known as moment of inertia about a line about the x axis. But what is this Ixy? This Ixy is something very different. This Ixy is minus summation I mi xi and yi, and Ixz is similarly minus I here mi and then xi and zi, right. So, these are the three symbols, and then Lx is equal to Ixx omega x plus Ixy omega y plus Ixz omega z, and you can similarly work out the y component of L and z component of L. And what you find is that Ly is equal to, let me write that again, Lx is equal to Ixx omega x plus Ixy omega y plus Ixz omega z. Similarly, you will get Ly is equal to Iyx omega x plus Iyy omega y plus yz and then omega z, and Lz you will get Izx omega x plus Izy omega y and plus Izz omega z, and the new symbols that I have written Iyx, Iyy etc. are the following: Iyy will be summation over I m and then zi square plus xi square. Izz will be summation over I mi xi square plus yi square, and then Iyx will be same as Ixy and Iyz will be same as Izy. So, everything goes over 1, 2, 3, 4 new symbols, Iyx I have written, Iyy I have written, Iyz I have written, and then okay, that was not written here, okay fine. So, this is equal to minus summation I mi and then yi and zi. So, this is written zx is equal to xz, zx I zx is equal to Ixz, and that will be minus summation I and mi and zi xi. So, I have written everything, Izz I have written, Izy I have written, Izx I have written, Iyz I have written, Iyy I have written, Iyx I have written. So, this is the relation between angular momentum components and this omega components. So, remember L is not necessarily in the direction of omega. Axis of rotation, angular momentum is necessarily in the direction of axis of rotation. This is wrong, it is not. Here is the relation, and in this relation you can write this relation in a matrix form. It is, you will write it as Lx Ly Lz, this column matrix equal to Ixx Ixy Ixz and so on, Iyx here, Iyy here, Iyz here, Izx here, Izy here and Izz here, and then this side it is omega x, omega y and omega z. So, this whole column matrix which gives you the 3 components of angular momentum vector, and here you have this column matrix giving the components of angular this omega angular velocity vector. The relation between this and this is like this. It is not L is equal to some constant times omega, right, it is this. This we write as L equal to, this whole thing is called moment of inertia tensor, moment of inertia tensor. This is moment of inertia of the object, of the body, of the rigid body about the origin, not about a line, about the origin. Okay. So, moment of inertia about the point, about the origin is needed to get the relation between angular momentum and this angular velocity. This quantity, if you wish, not a very standard symbol, but people sometimes use this with a double arrow, saying that this is not a scalar quantity, it is not a vector quantity as such, it is a tensor of rank 2. It needs 9 components, 3 to the power 2 components, and it is known as tensor of rank 2. That is this moment of inertia, and then this is omega. So, this is this relation you should know very well, that if you want the relation between omega and L, because omega is given to you, and then you have to connect this angular momentum with that omega and then torque with that angular momentum, that is the chain, and therefore, this relation one must know that this L is related to omega in this particular fashion.